maybe somebody will watch this video a bit later. Okay, first of all, as I think the majority of questions will be dedicated to final project, and as I see in here, I can see several questions to me about the final project. So let's talk a little about it. First of all, let's start with first question. Checking cells are missing in the notebook. Okay, so what do you mean? First of all, I can tell you some long story ago, but in some historically there was a system of there was some possibility to make there was some automatical checker, but there was a little problem. It was too connected to Coursera specific, so it was connected to some Coursera logic. So unfortunately, it can't be repeated here in LMS or just on your computer. So that's why we have no automatical checkers right now. So okay, so maybe it's my mistake that I forgot to delete several cells. Okay. So such how to check the tasks. What's the question? How to understand the correctness of your solution by your own? That's the question. Am I right? Unfortunately, there is no such possibility to compare your solution with help of some automatical checker. But first, you can. What can you do? In the majority of questions, you can check the correctness just by your own eyes. For example, you can tasks number 1, 2, 3. I think that they can be easily. We don't need some check for correctness. I believe that tasks like 4 and 5, for example, it will be much more convenient with. It's more easy to solve them using the automatical checkers, but unfortunately we have no such possibility right now. But at least you have possibility to check if your solution is correct by making plots. For example, when you compute the gradient descent, when you plot the errors, yes, you can check you can look if it's convergent or not, and it can give you the size of the error on every new step will give you a hint if your solution is correct. Like if the size of error if error just grows, when it means that your solution and your gradient descent doesn't work in a correct way. So, to be honest, I don't think that you lost too much with this without these automatical checkers. The majority of tasks can be easily checked just by eyes. So I don't think that it's a really big problem. I believe that it's some problem, but not so great. Size of error, should we look? First of all, a little about the logic, the idea behind this task. Tasks like 4 and 5, like when you use some simple gradient descent, without data transformation, without standardization. When you use a really simple metric for your mistake, and you a really simple model for a mistake, the size of your error can be really huge, and that's okay. So, like, to be honest, if I would check with tasks, I won't see, um, I will see no problem with really huge mistakes. Like, first 5 tasks is like playing in, how to say, like, you know, when which like playing in the sandbox and nothing more. Here you can get really huge values of mistakes. Even it's not a big problem if your experiments don't converge. Like, as you can see, you need to provide at least 2 experiments, and please, there should be at least 1 conversion. So you don't need to worry about the size of mistake. Like, that's not a machine learning course. That's just a course for calculus, and we want you to understand the idea behind the gradient descent. How it works, what's the logic of it. As a task number 7, when data will be transformed in a standard way, then you will use process of standardization of data. We expect you to achieve again, still bad results, but not so bad like in the task number 5. So we just want to see the progress of your algorithm. Just so please remember, we don't wait for great solution that will predict really well, that will give some golden standard in the machine learning. We just wait you to understand the idea behind the gradient descent, and we want to see what you can experiment with it. That's all. Is it okay? Looks like okay. How to calculate gradient descent? Okay, what variables in the code and are responsible for and the calculation logic? Okay, that's a nice question. As very popular when we talk about the about this lab. Okay, first of all, please can you write plus or minus in chat if you understand the idea of gradient descent. What is it and how it works? So, like, I don't understand how it works. Minus, like, it's clear for me. So plus, can you please type it in the chat? Like 1 minus, 1 plus, and what about the others? So it depends, I think, how much time I want to talk about it. What's the level of detaility I need to use if we talk about it, how calculate. Okay. So introduction to the final project, material for self-study. Okay, as you can see, we have some explanation how it works, like some a little talk about the idea behind the gradient descent. Okay, let's talk about it. So how does it work? It won't be an easy talk, but okay, let's try to discuss it. First of all, consider the following. We have some model that can make some predictions. Okay, let's generate some random data just by my eyes. Like, consider the following. Like, we have several vectors. Like for example, first vector is like 1, 2, 3. Second is 3 minus 1, 5, and the third one is I don't know, 6, 2, minus 3. Like, and consider the following: like the first two labels of every vector is data, and third coordinate is a value, is a label of this vector. Like, it's better to write in this way. So like for vector 3 minus 1 corresponds value of minus 5 of 5, and here we can, I don't know, and 6, 2 corresponds minus 2. Consider the following: like that's our training data, for example, and we have some have some linear model, but we want to build. We want to find the dependency, and we want to find the dependency and we want to state the dependency. How it works? And we have some simple model like linear model. So what means that we want to find some simple. We want to find some linear approximation for y, but depends on x. Like as you understand, it can be usually there is no such linear function that describes y by values of x. So, but we want to find the best linear function that fits our data. So what's I don't know what's the most classic situation in the machine learning when your data can be just described in the terms of linear functions. Okay, consider the following situation, like this one. And we have the model for your we have the model for your loss, like this one again, like MS here. So, and we want to find the best values of W of with parameters using gradient descent. That's like your own. That's like your task, but as you can see, it's something from Sandbox. So with really easy values of with very low amount of coordinates. So it can be, we can work manually with it. Okay, how can we do it? Consider the following: like we have some space of parameters. Like here we have some three-dimensional space. Like we have three-dimensional space of parameters. Like we have some axis for parameter with label 0, label 1, label 2. And how we can work with it? For example, we can start with some randomly computed, randomly taken set of parameters, like, I don't know, 1, 1, 1. Okay, and let's, does it fit well our data? Let's check. What prediction will we achieve using this data, and using this set of parameters? What's the value of a prediction? What's the value of a prediction we will get? What can you say? We have this linear model, we have this data, and we want to compute the value of prediction. Dear students, is it clear what I'm talking about? I'm just waiting for questions, so Okay, so can you say what's the value of the prediction? We have with data, we have with randomly taken set of parameters, we have with data, and what the prediction will be achieved. You can type it in the chat. Yes, that's great. Okay, of course it will be 4, just because if we want, we just need to compute this linear function with linear function, and we know the values of parameters 1, 1, 1, and we know the values of x of x1 and x2, 1 and 2. So here we will get something like with 1, and we will get 4. We can easily repeat this action. It can be a bit, annoying, but you know there is no possibility to explain it in a short time with good description, with good visualization. We can repeat this action again, and we will achieve that second label will be 3, the third label will be 6, and the last one will be 2, if I'm right. Yes. Okay, we know for this set of parameters we can compute the value of MSE, mean squared error. Like what is the formula for MSE? As you remember, we have this one standard formula to compute loss. Okay, we can so how can we compute it right now? We know that we have our loss equals to 1 over 4, and here we have sum of different the sum of squares of differences between true labels and our computed labels. So how can we compute this sum? We need to compute several differences. Like true label, first one, is 1, and our predicted label is 4. So here I need to compute the square of difference between 3 and 4. And repeat it again. 3 plus 5, 3 minus 5 in square, plus minus 2 minus 8 square, plus 1 minus 2 square. And maybe somebody usually computed, somebody has already computed, but like it looks like some terrible value, 1 plus 4 plus 100 plus 1, and we can achieve this value of the loss. Okay? So, as you know, big loss means that our prediction is, that our set of parameters is bad. So, we want to make it better. So, how can we do it? So, let's talk about the idea of gradient descent in a nutshell. So, consider the following. We have some space of parameters. Right here, right now, our point is somewhere here. Like right now we live at the point 1, 1, 1. Okay, yes? And what do we want to do? We want to compute we want to find some new point, some new set of parameters, such that the value of loss at this point will be smaller than the value of loss at this point. Like, consider the following. Imagine that there is some point, I don't know, like And here we have a value of loss like 106 over 4, and here we have value of loss like 21 over 4. As you can see, with randomly taken with point, as you know, I don't know what the value of loss here is 21 over 4 with some randomly written values. Like, our goal is to walk in the space, to have a walk in the space of parameters, just to achieve this point or some other point with smaller value of loss function. So we need to have a walk in the space of parameters, of values of parameters. How one can do it? So here we can find an idea how to compute it. Like as you can see, the idea is the following. What do we want from the loss? We want loss to decrease. Okay, yes? So what means that we want to find such point that value of loss is smaller. How one can do it? We can use gradient of loss. We can find gradient of loss. Like, you know, what's the idea of gradient? If gradient, if we have, for example, this gradient at the point 1, 1, 1, that means that in this direction, loss just grow. So that means that if we will walk in the opposite direction, it will decrease. So, like, so the idea is the following. That was some randomly. That was the first point. That was starting point. Like I don't know how to write it. Like label 0. And here we can come to some new point and we want to come to some new point such that we walk in the space of parameters in the opposite direction, in the inside direction that it will be opposite to value of gradient. Like gradient shows us to go like to the left if we want to increase the value of loss. So minus gradient gives us a direction to decrease the value of loss. So what do we need to do? We need to compute the value of loss at this point. Yes? And after that, we need to compute some new point. Like I use this bar to show it that's a vector. Like W0 is a parameter, and W0 with bar is a vector, is a set of parameters, is a first set of parameters. Okay, everything is clear. I'm afraid that talk isn't really simple, but I can see no reaction. It's a bit frightening, so I just...
Sorry, what vector W should we take? Is it computed inside the linear approximation law? When we take regression, we compute the coefficients and intersection inside of it, and we don't take random vector 1, 1, 1.
You have some different strategies to take randomly first vector. For example, you can take 1, 1, 1. So we don't wait you to build a good algorithm of machine learning. We just...
So that vector that should be passed to the task is random, and we can take any vector.
Yes, you can start with... yes, you can start, for example, with vector 1, 1, 1. Of course, you're correct, but practically that's a bad idea. So you know that the idea of finding a good starting vector, that's a complicated task. That's a part of the task of a gradient descent based algorithms. Like to find you need to find a good first approximation. You need to find the good logic to recompute alphas. You need good boundary conditions. You need plenty of things to build a really good algorithm. But we don't want you to write a really good algorithm. We want you to play in sandbox. So you can start with vector 111.
Okay. In the first one, yes, as you can see, the weights should be passed into the function.
Mhm.
Like in the upper one, the first linear regression, but they could be computed inside that function, not passed. The first task where
Task number 5, this one. Like it's first task with real gradient descent.
no, the linear regression one in the upper part. Yes, it's here. It's here. Yes, the loss is computed as W, the coefficients are passed inside the function, but they could be computed the linear regression function in the module.
So maybe I don't get something. Like we expect you just to write the. Here you just need to write the code how to compute this expression. Like when you have set of x and set of y. So
Yes, we can write from a scalar linear model,
For
and we
example?
can feed linear regression, and the weights, such coefficients, are computed automatically. We don't need to pass them inside of it.
to be honest, we expect you to write it by your own, but we want you to write it manually. Like, of course, as you, if you know how to work with libraries for machine learning, as you can see, all this library, all this task, all this project can be made with several strings.
Yes, of course, but such coefficients could not be computed like without it, or should be some like approximation like inside of it could be 111 for every
Like here,
very bad approximation.
I don't understand how the solution of the task, of this task, for example, number 2, depends on starting vectors and something like this. Like that's just function, that's just logic of processing of some data. Like you don't depend on data when you write a function.
Yes, I see. Here you can see the hint, and it is very bad hint, like 1 for every coefficient and for the intersection. It's okay, yes.
Is it convenient to add the x matrix to account 1? Yes, of course, that's a good hint, because you can see the idea of maybe I missed something, but that's like an idea to move to scalar products. Like here, as you can see, x is a two-dimensional vector, yes,
Yes.
and w is three-dimensional vector. So usually we want to rebuild our vector of to this form, because it will give us possibility to compute y as a scalar product, as a scalar product of this vector and this vector. So what's the idea of the hint? So we just
Yes, I see. Just we don't need to compute exact coefficients for the best fit. We just need to pass 111. Then it will be okay.
For example, yes. Okay, so in this sandbox task, we want to compute the, if we want to find the first approximation, if we want to improve our randomly taken vector w0, we need to compute the loss of the function. First of all, is it clear? Is it clear how to compute the loss function?
Yes, it's clear.
Okay, so when in this case I don't want to spend time and to compute it because it's a really annoying thing. So, but I just want to clarify, or maybe to focus on it. Like here, first of all, what does it mean? What does it mean? What we want to compute the loss of this function? As you can see, with value y with hat can be rewritten using the linear function that helps us to we know that predicted label is based on the concrete value of w, of x, and so on. So, for example, you can see that this function depends on w, on w0. So we can compute the partial derivatives by w0, w1, w2. We can build gradient and we can find some vector. For example, in my randomly taken, here my gradient is randomly looks in the left side, but it can be, but the correct vector can look somewhere else. And so we can compute the gradient of loss, but we can compute with gradient, and we can find some value of step, like some size of step, alpha. And we can, using this computed loss and with alpha, we can find new value for set of parameters. And we hope that this value will be better than the previous one. So we can repeat these actions with moves several times. And for example, we can one time we can have something like loop around some point. Like for example, our walk in the set of parameters can look like this. So that means that we will find a good point for we will find some good point for our algorithm. So what's the logic behind the gradient descent? Okay, is it clear? The key idea behind the gradient descent.
So each coefficient should be approximated like this?
Each coefficient. Yes, at the end of your walk you will find some point. So it means that you will find some set of weights.
That weight should be for each coefficient and for the intersection, as you wrote W1 bar.
Mm-hmm. Like, okay, first of all, you will compute.
It's for the one, and for the second coefficient, we should compute the same one, yes?
Yes. So, like, and we can repeat it with, like, here you can just see something like y plus 1, and here you can see something like y.
Oh, okay, and we repeat it until we are in some boundaries.
We have several ideas how to store the when to store the walk of your algorithm. usually we have the most popular ideas is to bound the amount of operations. Like you want to make 1,000 of steps, and that's all. Like 1,000, and let's stop. And second idea is to compute the size of gradient. Like consider the following: like you computed, as you can see, how big is your step every time. It has a value of alpha multiplied on value of loss of gradient. Okay, I will answer a bit later. What's the idea? How big is your step? It depends on value of alpha. We suppose you to use some randomly token uniform value of alpha, like for example, the simplest one, like, or you can take some another value of alpha, like 1, but we still don't want you to write the best algorithm in the world, just some playing in sandbox. Like it depends on value of alpha, and it depends on size of gradient. Like for example, consider the following. One can imagine it can help it can happen, but the size of gradient at this point will be large. So your step, this vector will be large, so your step will be large. And for example, at this point, value of loss of gradient will be small, so your step will be small. When you move towards some stable point, some local extremum, when with every step, the size of your gradient will be smaller and smaller. Every step you will achieve smaller and smaller values of gradient. That means that from when you will be really close to your stable point, to your extrema point, local extrema point, your steps will be really small, and there will be no significant difference between the previous one value of W with head, and between the previous one and new one, because your small is really small, your step is really small, so there is no big difference between this one and this one. So you can say that that means that there is no logic to prolong your actions. Like it can be a good moment to stop your algorithm. For example, so here you can see with ideas, like you can classic ideas is to you can choose one of these conditions, like to small gradient length, like we have already discussed, small enough loss function value. That's not really good hint for this task, for this concrete task, because you don't know what value of loss function is good for you. Like when you have some concrete precision to solve for your task, when you can you can assess the value of loss function that can be good enough. But here there is no space. There is no space to use this logic. And also we can check the value of WK for convergence. Like for example, that here W without head means the same as my W with head. So it means that you can compute the size of difference between WK and WK plus 1 on every step, and you can check if this difference is really small. So I suggest you to check the size of gradient and to limit the number of iterations. So for example, here in the code you can find here you can find some hint. We suggest you to stop this algorithm after 500 of operations. Of course, you can increase this number. Like, if you want, you can take 5,000 or 1,000, or you have a lot of freedom when you solve this task. And also, we suggest you to bound the length of gradient. Like, for example, if you can compute gradient, when you can compute the length of gradient. Like, you know how to compute the length of vector. You know that if you have some vector E, like this one, you can compute the length of this vector using this formula. So using this formula, that's a formula for the length of vector E. So, for example, you can bound the amount of your operations. Like, you can solve the algorithm if length of your gradient is smaller than epsilon. Of course, you can change the value of this epsilon, like with some. That's not a strict part of the task, like to take 1/100. Okay, and as I remember, there was a question: what's the logic of combined gradient in the fifth task? We have to change the values of vectors height. So what's logical congruent in fifth task? To add vk, and we have to change the values of weights. Look. So I need several seconds. So please give me this time. It looks like I weight losses. Okay. So look, what's the idea? We have set of weights, like all set of weights from the first moment of time. Set when we want to append here new weights. Like for example, what's the idea? What's the difference? Here we can find with set of weights corresponds to this weight plus this set of weights plus set of weights for this point, for this point, for this point, and so on. Like, we want to collect all the weights along the way. Why? Because at the end of the task, we want to save all our weights and all our losses. It will give us a possibility to build a plot. And
we add new weights to all weights, yes? As I understand.
Sorry?
We add our old weights, initial weights. We add new weights to our old initial weights, yes? So we do not change the initial vector.
Yes, we have some randomly taken vector. It can be really bad, but it's not a problem. After that, we can.
Okay.
After that, we can compute new vector. We can append this new vector to the vector weights, and we can compute new loss. So now we have some big. Now we have some set of weights, set of losses. Of course, first losses can be really huge. Of course, first vectors can be really bad. That's not a problem. because our goal is to visualize um, the logic.
How they change, yes.
Yes, yes, we want to look at the changes. We don't want, I want to repeat it again. We don't want to write a really good algorithm. We want to see how it works. So you will build a plot and you will see that, okay, first steps were really bad, but step number 100 will be something a bit better. And the step number 1000 or 500 will be like something acceptable. So here you have some set of weights, you have set of losses, you have a number of iterations right now, how many iterations you have already done, and you have a concrete weight just for this moment. What some mm, that's
So
all.
the last weight of weights, yes.
Yes, yes.
Okay.
Such, and now after that you can recompute. As you can see, we want to recompute. Oh, that's not a modern like. Sorry, slip of tongue. I just need to translate some simple word. Current, of course. Yes, of course. Like after that, as you can see here in the cycle, we want to recompute our current set of weights, our current loss, using the function from task number 2. And after that, we want to save our new weight and our new loss. So repeat it many times. I hope I've answered your question. Anton, what was your question, and everything is okay, I hope.
Yes.
At least I hope
Thank you.
it's a bit better. Okay, any other questions? Vladimir, it looks like you turn on your microphone, but there is no sound. Yes, for example. I just want to. Okay, one thing. One more thing I want to say. But for the task number 6, it's we expect you to write some simple functions that you can find in the standard libraries by your own in the majority of tasks. But task number 6 is an exception. So, for example, you can use it won't be banned to use the standard functions, like there is standard functions to build a standardization of matrix, like because it's a really annoying task to do it manually. So, but maybe it's not. Maybe it's not a big problem, but as you can see, there are no points for this task. It's just an intermediate task for the following ones. So if you want, you can use standard functions to compute it, but of course it can be done manually. But you can use standard function.
So like standard scale from
Yes.
Stallone?
Yes, for example, you can do it. But of course, I think that you know that we can just compute the average of every feature. We can easily compute the set of averages. We can extract it from your data when we can divide it over standard deviation of every feature. So, but for example, but you can use standard scale.
Okay. What is the deadline for this task?
Deadline, as I remember, 15 December. Like you still have 6
okay.
days to compute it. Like, yes, it looks like I'm right.
Yes, it wouldn't be moved to tomorrow. Yes.
Sorry, and
It wouldn't be moved to tomorrow. Like in Python course, it is tomorrow is the deadline for all the course, and it's for the last task.
I have no. No, I have no such ideas. I have no.
Okay.
I don't want to.
Okay, thank you. If it is 15th, it is great. It's okay.
So, sounds great. Okay, it's great, but it's great. Okay, it can be when certain losses are increasing. Yes. It's yes, of course, it's possible. It's possible, but sometimes because consider the following: like we have some great value of. Imagine that we have some huge value of loss. So, and we need to make a great step in this direction. Like, if we want to increase the value of loss, but we want to decrease, so we extract this value of loss. But our step is really, for example, it can be really huge. Like, function is decreasing in this part of direction. Like here, here the value of loss is decreasing, but after that it starts to increase, and we can get that this point has a bigger loss than this point. So it's possible, it can happen. So that's not a problem of implementation, but some problem that can happen. Okay. Do we have any more questions?
No, thank you.
Okay, it looks great. So if you have no questions, I think that we can finish our webinar. It looks like we discussed a lot. I hope this webinar was useful. Thank you for visiting the webinar. Okay, so I finish in this case I finish the demonstration of screen, and I finish the recording.